Hello viewers, in this video we are going to discuss true false, which is based on the rules in numerical computation. So here the first true false question is minimize the number of arithmetic operations whenever possible. So yeah, this is true. So there are several reasons why it is beneficial to minimize the number of arithmetic operations whenever possible, and these like efficiency, accuracy, robustness and memory management. So overall, minimizing the number of mathematical operations can lead to more efficient, accurate and robust algorithm with lower memory requirement. Now the second is avoid taking the difference of two nearly equal numbers whenever possible by alternate formulation of problem. So if it cannot be avoided, then take the difference before doing other operation. So this is all again true. Like for example, if we are taking here a, which is value is a is equals to 1.000001 and b is equals to 1.00000002. So here in this case the value of c, which is the result of subtraction between a and b, may be lost due to limited precision of floating point arithmetic. So this can lead to inaccurate result and numerical instability. Thus, to avoid this problem, it is recommended to use alternate formulation of problem that avoid taking direct difference of these two nearly equal numbers. Now the third one is adding or subtracting numbers. Start with the smallest number and work with number in ascending order. So yeah, this is true. So adding or subtracting numbers, starting with the smallest number and working with number in ascending order, can help to improve accuracy and numerical stability of computation. So in this PDF you can see that here some variables with the initialized value are given, and here are the result when we are adding them in descending order and we are adding them in ascending order. So in this case, adding the smaller number first reduce the impact of rounding errors and improve the accuracy of result. That's why it is preferred to add or subtract number which are starting with smallest number and then in ascending order. We proceed in ascending order. So now the fourth one is do not formulate an algorithm which tests whether a floating number equals 0. So this is true because because whether a floating point number equals 0 or not, floating point number are not exact and their value may be subject to rounding errors. So due to limited precision in floating point arithmetic, it is difficult to represent certain number exactly, including 0. So this means that even if two floating point numbers are mathematically equal to 0, their representation in memory may be different due to rounding error. Now fifth one is ill conditioning of problems is normally due to improper formulation and can be eliminated by careful reinforcement of problem. So a practical way if detecting suspected ill conditioning is to alter the parameter by small amount and observing their effect on the solution. So yeah, this statement is also partly true because ill conditioning of problem can be due to improper formulation, but it can also be due to the nature of problem itself. Yeah, because ill conditioning, what it means, like ill conditioning means that a small change in the input or parameter of the problem can lead to a large change in the output or the solution. So this makes the problem difficult to solve accurately and can lead to numerical instability. Now in sixth point, after a numerical algorithm is obtained, check if it can lead to numerical instability. In such algorithm, error group in each step of the calculation. In such case, reformulate the solution procedure to get a stable numerical algorithm. So yeah, this statement is also partially true. So numerical algorithm can indeed lead to numerical instability. So where the error grow in each step of the calculation, this can be due to variety of factors such as ill conditioned problem, numerical round of error or instability in the algorithm itself. In 7th point, it is given that if severe rounding errors and consequent loss of significant digit is anticipated, and if no alternate formulation to avoid this is possible, then carry more significant digit in the critical calculation using floating point number in double precision mode. So in this mode, the length of the mantissa is twice that of the other floating point quantities. So yeah, this statement is also true. So severe rounding errors and consequent loss of significant digit can occur in numerical calculation, and particularly when dealing with quantities that are widely in magnitude, or when performing operations on values they are close to limit of the machine precision. So in such case, if no alternate formulation is possible to avoid this loss of precision, carrying more significant digit in critical calculation can help minimizing the impact of rounding error. So in the eighth statement, it is given that double precision require large memory space and slow down computational error. So yeah, this statement is also partially true, because double precision does require memory space than the standard single precision. However, whether or not double precision slow down calculation depend on the specific content and computational requirement of the algorithm. So in some case, double precision may be necessary to achieve the desired level of accuracy or to avoid numerical instability caused by rounding error. So in this situation, the benefit of increased precision may outweigh the additional memory requirement and computational cost. And in ninth statement, it is given that in third iteration of finding a square root of 5 with starting point 7 using Newton-Raphson method, the relative error is 0.0013. So here many certain things are not given, like to answer this question. So based on the given information we can make a guess, and here you can see that in this PDF by assuming things we have proceed this question, and here the third approximate of the a square root of 5 using Newton-Raphson method with a starting point of 7 and relative error of 0.0013 is approximately 2.24119, which is true. Now in 10th and last statement, it is given that the iterative method are compared on following parameters. First is rate of conversion, second is amount of computational efforts per iteration, and sensitivity of the method to be to the starting value and intermediate value. So yeah, it is also true, and we will see it. So in first rate of conversions, so yeah, the faster the rate of conversions, the better the method would be. Now in second point, it was given that amount of computational effort per iteration. So yeah, it is referred to the amount of computational required to obtain the next approximation in the iterative process. So a method that requires less computational effort per iteration is preferred. Now third is sensitivity of the method to the starting value and intermediate value. So yes, this referred to how sensitive the method is to the initial guess and intermediate value used in the iterative process. So now we have solved and discussed all the true false in this question. So thank you for watching this video. Thank you.